Good afternoon, everyone. Welcome to the module week 6 problem solving session of the course Ultrafast Laser Spectroscopy. Here we are, and uh, today uh, today we'll be discussing some more problems which are related to the topics that were covered in week 6. Since a few people are still like they're we'll wait for a time of we'll wait for some time for the people to join and then we'll start. Yeah, so now I'll be presenting my screen to you all and then we'll continue with our problem question solving. Okay, so as I said, this is problem solving session number 6 for the course Ultrafast Laser Spectroscopy. So here we'll be starting our solving the problems which were given in the assignment 6. So starting with this, question 1 is the Bragg regime is associated with the options to this question are lower frequency of acoustic wave, shorter interaction length, zeroth order diffraction, and cavity dumping. So first of all, I'll explain each of these terms. What are these? So the first one is the lower frequency of acoustic wave. Okay, so acoustic wave, something that is related with the sound waves. Shorter interaction path, basically this relates to the interaction of the light beam and the, or you can say interaction between the light beam or the sound wave with the medium. And zeroth order diffraction, this refers to, like, suppose we consider any medium or any particular structure with slits or gratings in it. Then the diffraction is the process which occurs with any kind of wave. And cavity dumping, this topic we'll be studying or we'll be discussing later in this session. So, coming to this, what is Bragg regime? Actually, in the previous session, we had also talked about one another regime, that is called the uh, Ramannath regime. Okay, so what is here? They are talking about the Bragg regime. Yeah. So basically, what the cavity dumping is. Cavity dumping refers to when you need only a certain frequency of light and then you eliminate the others. So, Bragg regime refers to, suppose you consider this particular media and these bars represent the region with high and low density. So, basically this whole unit, this acts as a diffraction grating for the diffraction of the wave or the light beam or the sound wave. So, talking about the Bragg regime, if any incident light is, if the beam is incident on any medium, two things happen with it. And the first of all is either it passes unnoticed directly straight with the original frequency omega naught, or it may be deflected to a certain angle, that is, and with a different angular frequency, that is omega naught plus this omega. So this omega refers to the angular frequency of light beam, and this omega refers to the angular frequency of sound. So there is some change in the angular frequency of the incident light beam. Okay. Now, uh, and also this acoustic wave, the sound wave which we are talking about, which is a longitudinal wave, it has an angular frequency of omega and the wavelength of lambda. Now, in this cavity dumping, what happens is uh, we prepare a Bragg cell, okay, and we work in the range where this L, which is the length of the particular this passive mode locker which we have kept inside the cavity, its length should be greater than the lambda square upon 2 pi lambda. Here lambda is the wavelength of sound, and this lambda is equals to wavelength of light. So particularly if you want the process, that is this cavity dumping, you need to work in a region which is the Bragg region. Therefore, each of these values should follow the this relation which we are writing. Okay, and thus we can also say that if you want this length to be greater, you need this to be greater and this to be smaller. Okay, so this is the case of Bragg region. Then in a short, I'll also be explaining what is the process of cavity dumping. So what happens is, initially from a direct a beam with the initial, actually this E naught refers to the electric field component of the incident beam. So when this beam when this incidents over the, suppose this light beam incident over with the frequency of E naught, we have two concave mirrors that are placed at a position where this M2, like the this Bragg cell, is kept at the focus of M2 and the center of M1. Now earlier when we have studied different ray diagrams, what we have studied is something that passes through focus. Like suppose this is a concave mirror. So say a light beam, it passes through focus of something, then it will go parallel to infinity. And second thing, if it passes through center of curvature, say this is C, it will retrace its path. Okay, this is the relation they have been using here. So suppose E naught is the wave, is the electric field component of the incident beam. So when it incidents here directly straight, it is reflected back. Okay, it is reflected and therefore it passes through this RF cable and there is some change. Meanwhile, what we thought about cavity dumping is when the incident beam of angular frequency omega naught and wavelength lambda is incident or it passes through the Bragg cell. Some part of it goes straight and with the same angular frequency omega naught and the other part it gets deflected and also possess an angular frequency of sound, and that can also be written as omega naught plus minus n rho omega. Okay, so this has a change value. Now what they have told is when it incidents here and it passes through focus, some part of it gets deflected and some part of it goes straight. The part that goes straight is denoted by E2 and the part that is deflected, that is denoted by E1. Again, what happens, since we can say that this is this Bragg cell is kept at the center of curvature. Therefore, both of the beams will retrace their path. And how they will retrace their path when the E1 comes back? It is also again split because of this Bragg cell into two components, E1 prime and E1 double prime. Also, the same way E2, some part of it goes straight and some part of it goes deflected with this angle, and therefore the part which goes straight is E2 double prime, and the part which is like sorry, the part which gets deflected from its path is E2 prime, and this is how the total what you get that passes through the prism is the sum of this E1 prime and E2 prime. Okay. Now, coming back to our question, what is asked in our question is Bragg regime is associated with. So, Bragg regime, first of all, zeroth order diffraction, yes, it is one of the characteristics. Although, so the first of all, Bragg regime, for the Bragg regime, as I told you, see here you can see from the relation the L should be greater than lambda square, capital lambda square upon 2 pi lambda. Okay, so this is L is the interaction length anyways. So as you can see from the relation, the L should be greater than this value. So as this is one of the MSQs, like this can have two or more right options or one or more right options, we can say that first of all it is associated with a longer interaction path and not a shorter interaction path. Got it? The second one is lower frequency of acoustic wave. Okay, so see this relation. Acoustic wave means this, or acoustic. This is the acoustic wavelength. Okay. Now, if you want L to be greater, you need this to be greater, and if this is greater, the frequency will be shorter since wavelength is inverse of the frequency. Okay. So this is again not the right answer to this question because okay, yeah. So this can also be the right, yeah. And the third one is zeroth order diffraction. So yes, this is correct. Because if you talk about Bragg regime, when you just pass the incident beam through this Bragg cell, what you get is it has a longer interaction path. And second thing, you do not get higher order. Higher orders of diffraction is not seen. What you see is only zeroth and first order diffraction. Okay. So yes, Bragg regime is associated with a zeroth order diffraction. And second thing, this whole process is called as cavity dumping. Now, what is the advantage of doing cavity dumping? One of the advantages and the best advantage is when you talk about this, say E1 plus E2 prime you get outside through the prism which goes like this straight, okay, till here it reaches, it gets refracted and then it goes through a straight path and therefore reaches out of the cavity. So this is the thing, and therefore we get the required beam out of the cavity which has the component E1 and E2. Now the whole criteria is that even what happens to this E1 prime and E2 prime. This E1 prime and E1 double prime and E2 double prime again get circulated within this whole circuit, and this is how we have no loss of intensity. So this is the main advantage of using cavity dumping, no loss of the intensity or the light. Okay, so this is energy friendly process. Okay, as we can say that the light which we want comes out of the cavity safely, and the light which we do not need again gets circulated back in the cavity. One more thing related to this whole process is this is the Bragg cell. This Bragg cell has some regions with different density. The darker region shows the higher dense medium, and the lower white colored region or the light colored region shows the lower density medium. Okay. The second thing also is, see this, what happens to this acoustic wave. This acoustic wave is applied perpendicular to it, and if you remember we had studied this acoustic wave of acoustic acousto-optic modulator. So this is something same, but only the relation has changed. Earlier we used to work in the Ramannath regime, and now we are working in the Bragg regime. Now in the Bragg regime, basically this criteria is changed. The length of the cavity is something which should be greater than the particular relation. Earlier in Ramannath regime, if we talk, the length was smaller. But now in case of cavity dumping, we have to apply a sound wave that is perpendicular to the wave of to the to the intensity of the incident beam. This incident beam talks about the light beam, and this acoustic wave is related to the sound wave. This medium can be something like earlier they had taken, that is the water. Now what happens? There used to be a transducer and here used to be a quartz crystal. When they used to apply a sound wave perpendicular to the light wave, there used to be compression and rarefaction in this medium, which could divide this medium into different halves, like of basically of different density. The region of compression is higher density and the region of rarefaction is of lower density. Got it? So now again I'll try to summarize all the things which we told. Yeah. So basically, cavity dumping is just opposite or some way. Earlier in the earlier session, we talked about the passive and active mode locking, where we used to work in the Ramannath regime. Here we are talking about the Bragg regime. Okay, and Bragg regime, what? what is the criteria, that we'll be discussing later, but first we'll see what is cavity dumping. So cavity dumping is something where cavity dumping is something where, see, here is the where here is the Bragg cell. The Bragg cell is something that comprises of a Bragg cell is something that comprises of a section a region of a material, and that may be a crystal, but normally what we studied for acousto optic modulator, that was say that was a container that was filled with water. What we do is we incident the beam with the light of a particular wavelength and angular frequency at a certain angle. Now what happens is, and we also apply a sound wave, that is the acoustic wave, that has angular frequency omega and the capital lambda wavelength. Now what happens, as the incident beam passes through this, the incident beam or some part of the incident beam passes straight with the angular frequency omega naught, and the other part gets deflected by an angle theta. Okay, this angle is the theta, and this is also called omega naught, and this is also modulated frequency, angular frequency, which can be given by omega naught plus minus n into omega. Okay, capital omega. Now this capital N omega comes from the acoustic wave, or you can say the sound wave. Now also what happens here in the Bragg regime, the length of this whole Bragg cell is taken to be as L, and this L is something that governs or is the criteria of the Bragg regime. Whenever you need to do cavity dumping, you take a Bragg cell, and the it should follow the particular rule which is suggested and is called as the Bragg regime, that is L. The length of the cavity should be greater than the wavelength square upon 2 pi lambda. Here wavelength is here the lambda, capital lambda, is wavelength of sound, and small lambda is wavelength of light. If you want to follow this entire procedure, you need something, that is the L should be greater, and that L can also be called as the cavity length or the interaction path. So L is the interaction path, and according to the Bragg regime, it should be longer. Okay. And what is this interaction path? This is interaction path of light. Okay. So, and the second thing is, because of this diffraction, the change in the or this medium which works as the diffraction grating, there is change, like the diffraction occurs, and like it gets the deflection also occurs at some angle theta, but because of the longer interaction path length, you do not get the high order diffraction. So you do not get them. What you get is only zeroth or first order diffractions. Only these two you get. Okay. Now one more thing is, here I also in very brief, in a few words, I taught what cavity dumping is. So basically in the cavity dumping, say this is the E naught, and you need to say change the frequency or modulate it. So what you do is, if E naught is the intensity of the beam that is incident, and E naught is not the intensity, E naught is the electric field vector. So basically, because of the concave mirror, the light gets deflected. Now again, the thing is, the position of this Bragg cell is at a distance of focus from M2 and at a distance of center of curvature from M1. When it goes to M2, after becoming reflected, it passes through the Bragg cell, and this happens what we have seen in this diagram. Like it gets, some of the part gets goes straight, that is E2, and some of the part gets deflected. Now, as soon as it passes back again through the Bragg cell, again what happens? This E2 some part goes straight, that is called E2 double prime, and some part get deflected, that is E2 single prime. Again, the same thing happens with E1. Some part goes straight, and that is called E1 single prime, and some part changes its way, that is E1 double prime. Although the notations which are given to each, they are not according to the same thing which is happening to both of them, but in order to avoid confusion, we say that the total intensity of light that comes out is the sum of E1 prime and E2 prime, which then passes through prism, say goes straight, gets refracted, and goes out of the cavity back straight. In this case, the entire advantage of the whole process is that the E1 plus E2 prime, which is just refracted, does not lose the cavity. Like there is no loss in the intensity of light. The light is itself in the cavity and is again diffracted and passes through the Bragg cell. So this is the whole thing that happens. Now, related to it, the only relation that was important if we work for cavity dumping is L should be greater than lambda square upon 2 pi lambda. From this relation we got to know that if you want L to be greater, you need actually the longer interaction path, and that is what is asked. But the Bragg regime is therefore associated with a longer interaction path, which is not true for the option given here. The second thing is, in the case of Bragg regime, when something passes through the Bragg cell and the whole process occurs, we only get zeroth and first order diffraction and not the higher order diffractions. So therefore, zeroth order diffraction is the only thing which we see, because first order anyway it is not given in the options. The third is, in this whole process is followed when we talk about the cavity dumping. Okay, so these two are the right options for this question. Now again, uh, we'll go, if any one of you have any doubt in this question, we'll discuss it, or else we'll proceed with the second question. Okay, we'll go to the next question. So the next question is, given that K is an integer, cavity dumped output of a pulse laser is maximum when? Now, what is the conclusion or summary to this? When we talk about cavity dumping, something that comes out or the output is E1 prime plus E2 prime. Okay, and that goes on through this prism and just gets out of the cavity. But if you talk about the whole thing, there is a relation which we had derived from E1 for the value of E1 and E2. And how does it affect the intensity? So this is a long derivation where we have taken E naught, and E naught is equals to A naught e to the power I omega t, where I is the iota, omega is the angular frequency, t is time. A naught is the value of amplitude. So what happens is, if you talk about E naught is the electric field component of the incident light. The output field, on the other hand, is given as E1 prime plus E2 prime. This we had studied from here. Okay. Diagrammatically also, it is easy to understand how this E1 prime plus E2 prime thing. Now, using all the relations, what we could get is the total value for this is E output is the sum of E1 prime plus E2 prime, which is given by the relation 2 E naught root eta into 1 minus eta. And 1 minus eta we got from the relation eta is equals to I diffracted upon I internal. Okay. So the intensity of the diffracted beam upon intensity of the incident beam. Therefore, we got to know this is the relation. Now, one more thing that was we had to talk about, what is the modulating function for a cavity dumper. So for a cavity dumper, this part is the modulating function. Okay. So this is the modulating function, and the value of phi also we can calculate. What is phi? Phi is the phase difference. This omega stands for the angular frequency for sound, and phi s is the phase difference for sound, and so on. So actually, the conclusion is the intensity is the square of mode square of the output of the this electric field. So when you conclude and we come to the relation, we get this relation where intensity is equals to 4 E naught square eta into 1 minus eta 1 plus cos 2 omega t plus phi s plus phi. Okay. Now, this, keeping this aside, this is our modulating factor. Okay. What is the modulating factor like? How it will change when you will get the minima and when you will get the maxima. Keeping the other things, they are almost constant. This is the factor that changes. And how it changes? Because of the values of cos 2 omega. Okay. So, how do we decide it? So if the question here was when k is an integer, the cavity dumped output laser is maximum when. Okay. So if this is the factor that decides the whole value of the intensity, one thing we can surely say that if one is constant only, this is the factor and on its value depends what will be the maximum value. Now when you talk about the value of cos theta, the value of cos theta is maximum at 1 and not more than that, and minimum comes cos theta minimum, and it comes when the value of theta is 0. But if you keep the value of theta to be 0, then what happens? This entire unit turns to be 0 and the intensity will be 0 anyways. So you cannot consider it to be 0. Okay. So what you need to consider, we can consider it as it can be any integer. Okay. So therefore, for the maximum value, what is the rule given? Is first maximum for the maximum value. So for the maximum value, cos theta should be 1. 1 or but or greater than 0. Okay. When it is 0? The value of cos theta is 0 when the value of cos 90 is equals to, okay, value of cos 180 is equals to minus 1 and value of cos 360 is again equal to 1. What we can say is the value of cos 2 omega t plus phi s plus phi. This should be equal to some value that is equal to k any integer, but that should not be equal to 0. Okay. Therefore, k can be an integer. Okay. What we were asked in a question, given that k is an integer, cavity dumped output pulse laser is maximum when. Okay. So if the whatever we got from the relation, the I output is maximum when this value, and this value omega t plus phi s plus phi, it is equal to some value of any integer. So this is the relation for the maximum. Okay. Again, I just want to say here we had studied that E1 plus E2 is the total intensity of the output field. Okay. Now from this equation, we also got a total mathematical relation by summing up all the values of E1 and E2, and what we could get is this I intensity is the sum of I intensity is the square of this electric field vector, and therefore the total value is 4 E naught square eta 1 minus eta bracket 1 plus cos 2 rho t plus phi s plus phi. Okay. Now again, what we could say is the factor that governs or that rules whether we get a maxima or minima is the only one, that is this. Why? Because the other are constant. Now, if you talk about the maximum value of cos, the maximum value of cos is 1. Okay, but if you talk about 1, then you need to keep all of these 0. So instead of keeping these as 0, because then anyways the intensity will be 0, we can also say that the value of 1 plus cos 2 omega t plus phi s plus phi, it should be like phi s plus phi, it should be some integer. Okay. Also, if we want to say about the minima, then what we can say is it should be equal to k plus half. Okay. Then if you talk about minima, this is the relation for maxima. Thus, for maxima, first of all, the relation is I intensity is equals to E naught square is equals to 4 E naught square eta 1 minus eta 1 plus cos 2 omega t plus phi s plus phi. Okay. And thus, this is the modulating factor or function. Also, the value should be some integer, and thus the value of and that integer say is k. So therefore we can say for the maximum value omega t plus phi s plus phi is equals to some value k. If you talk about minima, it should be omega t plus phi s plus phi is equals to k plus half or minus half, k plus half. Okay. So for minima we got, for maxima we got. Here the answer to this question is for the pulse laser is maximum when phi rho t, sorry, omega t plus phi s plus phi is equals to k. The relations are all wrong. Okay. If you want me, I can write this relation in fair so that like in a clean manner so that it is visible. Let's wait, I'll rub the extra things. Okay. This is maximum, this is minimum. Now, if anyone has any doubt in this question, we can go on with this, and or else we'll proceed with the next question. I'll give you a time of 1 minute. Yeah, okay. So now we'll go on with the next question. The next question is also something that is related with the which we have discussed. So the modulating function for a cavity damper is 1 plus cos rho t, 1 plus 1 minus cos rho t, omega t, sorry. Second is 1 plus cos 2 omega t. The third is 1 minus sine 2 omega t. The third one is 1 plus sine 2 omega t. Actually, not to get confused, what they have given is the entire relation is 1 plus cos 2 here in the bracket omega t plus phi s plus phi. But here they have converted this whole into this is the major factor, so they have written as 1 plus cos 2 omega t. That's it. The other two terms they have not given. So basically the relation is 1 plus cos 2 omega t. That is the modulating function, and thus the right option to this question is 1 plus cos 2 omega t. Okay. Now if anyone has any doubt in this question, we can like related to anything, we can wait for a time and then we'll proceed. First of all, talking about cavity dumping, here we had started. First of all, for the cavity dumping process, cavity dumping means when you incident any E naught incident beam uh, on the in on a cavity passing through the Bragg cell, what happens is the total what you get as the output beam, that is the sum of E1 prime plus E2 prime, which is the sum of the diffracted beams. Okay. Now also there is a second thing. This Bragg cell was kept at focus from M2 and at the center from M1. Also, if you talk about the Bragg cell, whenever the light beam of intensity say I naught or E naught is the electric field vector when it passes through the Bragg cell, the initial change that happens is it gets diffracted into two beams or split into two beams. One part of it goes straight without getting diffracted, while the other part it gets diffracted at some angle theta, which has the frequency of omega naught plus omega capital Omega, which is the contribution from the acoustic wave. In the Bragg cell, the acoustic wave is something which is applied perpendicular to the incident light beam within this Bragg cell. When the two waves interact, they interact constructively following the Bragg's law, and therefore the length of cavity is something uh, that also follows a relation, that is L is greater than lambda square upon 2 pi lambda. A lambda was the wavelength of light, and the small lambda was the wavelength. Sorry, capital lambda was wavelength of sound, and small lambda was the wavelength of light. Second thing, when the incident beam passes through the Bragg cell, only the zeroth and first order diffractions can be seen. The higher order diffractions are some missed. When this particular phenomenon happens within this cavity, what happens is the output beam has E1 plus E2 total intensity, which then goes out. When you talk about the intensity of the output beam, that is derived by the following relation, where this following relation, the intensity or the electric field, the total intensity is the square of the output electric field contribution of the output beam, which has this all keeping these all the constant. This is the function or the factor that affects the value. Deciding this, we had formed that the maximum value, how to derive the maximum value. The maximum value can be any case some integer, and the minimum value should be 0. Okay. Now also, sorry, minus 1. Then also we told that since the other things are constant, the value of this omega t plus phi s plus phi should be equal to some integer k, and that is how it will give the maximum value, and the other will give the maximum value when it follows the relation, this, the omega t plus phi s plus phi is equals to k plus. So this is what is covered in the first question. For the first question, the answers were zeroth and order diffraction and cavity dumping, because the longer interaction path is so this option is ruled out. Why? Because we need a longer interaction path and not shorter diffraction interaction path. And if you talk about the lower frequency of acoustic wave, so this is also not the correct option. Then talking about the cavity dumping, from the equation we could derive the relation that y, the for the maximum value, what should be the value? That should be omega t plus phi s plus phi, that should be equal to some integer. So was the answer to the second question. Rest all the options, they are incorrect. And actually this is MCQ and the other one was MSQ. And we also studied this as the process of cavity dumping. The third question was phase modulating function for a cavity damper. So phase modulating function, from this equation itself we could say that this particular thing, this is the phase modulating function. Okay, so this is the thing, and therefore we can also write it to be as cos 2 omega t. Okay, in short, ignoring these two terms. Got it? So keeping these two terms behind, only this is the total answer. Then we'll go to the question number 4. What does the question number 4 say? In the example discussed in the course, the focal cell acting as a Q switch rotates the polarization of light by. Actually, this focal cell is something which we have studied in this module, and Q switching we have studied earlier. But something focal cell acting as a Q switch we have discussed in this module itself. So, for a brief introduction, I have kept this. What is a focal cell? So, basically, with starting with this focal cell is something made up of focal cell is something made up of non-linear optical material. Okay, so nonlinear optical material means, uh, earlier we had studied something that is second harmonic generation, where a light beam of 2 lambda say wavelength is converted to its exactly half, that is the second harmonic generation, but the frequency of omega is converted to omega. This was what we had studied. We are talking about focal cell. Something is a medium that is made up of some nonlinear optical material. Now suppose we input a polarized input wave through it. This is an isotropic crystal. This is what we call it as nonlinear optical material. And an isotrope is something which means that the arrangement within the crystal of the molecules that is not in the same pattern, that is not isotropic, and which leads to the second order effects. Okay, when you pass the polarized light, either it goes straight as the output will, but this does not happen if you apply a voltage that is perpendicular to it. So second thing is what they did, apply a perpendicular voltage. Okay, what happens if it is polarized light, say, so this light is split into two components depending on the depending on the applied voltage. The light is split into two components. Okay. Now suppose I apply a potential at which the light is divided into two, say equal intensity of right and left-handed circularly polarized light. Okay. So that is what is called circularly polarized light, which has equal left and right handed circularly polarized light. Okay. As you can say this is the equal amount of right and this is amount of left. So it appears to be circular and that is why it is called circularly polarized. If say right-handed component ER and the left-handed component EL, it has somewhat difference in the value. Say EL is greater than ER, then what you get is elliptically polarized light. Okay. Now here is what the focal cell does. Focal cell, if say light is vertically polarized light, then say focal cell will deflect at an angle of some angle. You can say this angle to be 20 degree or 30 degree or 40 degree or depending upon the applied voltage. This is the applied voltage. Okay. Now here, in this question, the focal cell acting as a Q switch rotates the polarized light bulb. Now what is this Q switch? This also will be discussing. Got it? What is the focal cell? Focal cell is electro-optic modulator. Electro-optic modulator is something that changes the polarization of the light that passes through. Suppose the polarized light is as an input through the focal cell. What you get is when you apply the voltage, there is change in the polarization of light. Now, suppose this polarization of light was totally vertically polarized. What happens when it passes through it and comes out? It is bit diffracted or say polarized by an angle, or there is change in the polarization by some angle which has a non-zero value. Talking about the Q switching, what is Q switching? So here we have used this focal cell. Okay, what is this focal cell and what is this Q switching? So if you remember, so far we had talked about Q switching in the previous some module where we talked that for the mode locking of the laser we need Q switching. Okay, so Q switching was used for mode locking, and this Q switching can be done by a focal cell also. How it is done? That we will see. Now Q, suppose what we have done, we have introduced it with some frequency of light. Okay. When light is incident on this acts as the amplifier. What happens is this light it passes through this mirror, reflects back and passes through a focal cell. At this focal cell, the light beam say it is rotated with some angle. Okay. Now after rotating to some angle, it goes through this mirror and again reflects and comes back to the focal cell. When it comes back to the focal cell again, it is again refracted to certain angle. Okay. Now after this, what happens? When it passes through the amplifier, we can say there is certain angle only or there is certain polarization only at which this amplifier can allow the light to pass through. If it allows, then it again goes through the mirror and therefore passes through the cavity in to and fro manner. And through this, the Q switching occurs. Okay. Through the Q switching, we can also get a giant pulse. Say if we feed it with intensity, say this, what we get in the output is something great, something with a very high intensity. Now, how this is produced? What I can say is initially, say this cavity is open. Okay, cavity is open, which says that say this light is passing through the shutter and coming back. Because of this, what happens is the cavity loss happens. That is, light moves off. So we can say that the only loss. Now what happens as we increase. Now one more thing is, how does this focal cell work? Okay, so the first thing was, say the voltage is off. If the voltage is off, the focal cell simply works as a refracting medium. Okay, in this refracting medium, what happens? The our light, it passes through this focal cell. It does not get polarized, or change in the polarization does not occur. It goes straight and then passes through the amplifier. Okay, this is the total case. Okay, it passes to and fro through this amplifier and goes straight. This happens when voltage is off. Okay, now what happens? The second thing is, when this whole say this first of all, when this voltage is on initially, because of the polarization, the light used to come to and get refracted. Okay, so this is the case of total loss. Now what happened? We have turned this off. When this is off, the light passes to and fro through this medium. Now with time, what happens? This loss, it has a maximum value, but slowly the gain increases. Why gain increases in the amplifier? Because now what we are doing is, when it passes through the cavity, since the voltage is off, the focal cell does not allow the polarization. This unpolarized light passes through this medium to and fro. Okay, because of this, the gain is increasing and therefore reaches to a maximum value. Okay, meanwhile, as the gain reaches a maximum value, after saturation, the value of the loss decreases, and thus when it reaches maximum, the cavity is switched on, or the voltage is switched on, and it the 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 light beam that again gets reflected out, and what we get is a giant pulse. Okay, so as soon as we open the cavity, the value of gain, it decreases, and simultaneously there is a giant pulse which we get. So what I told is, first of all, in the Q switching, what happens? Through the Q switching, a smaller wave pulse can be converted to a giant pulse. How does it work? The one with the dark is called as the totally reflecting mirror, and this is the partially reflecting mirror. The only medium that through which the light can go is this refracting medium, that acts like a medium with certain refractive index. Initially, say we say that the voltage is on. When the voltage is on, the focal cell is in function. So what happens, if you incident the light with something? It goes straight through this way, passes through the amplifier, goes through the focal cell. When it goes to the focal cell, because of the polarization, it gets bent to some extent. Say it was horizontally polarized, it bends to some extent. Then it goes to the mirror. Without any change in polarization, it returns back or retraces its path. When it retraces its path, say initially it was diffracted at an angle of 45 degree, it is again deflected at an angle of 45 degree. So what is the total now? It is, suppose it was horizontal, now it has turned to be vertical. Okay, and because of this, now it cannot pass through the amplifier, since it is at something that is called the Brewster angle. Because of this Brewster angle, something that is this amplifier allows only the light of certain polarization angle to pass through it. Not all of them are passed. That's why because of this Brewster angle, the light that total light that passes through it once is then again reflected out. It is refracted and not does not pass through the amplifier. So this is the case of total loss. Now what they did in the case of Q switching is they shut this off. Okay, so now this is off. When this is off, this just acts like a medium. This does not hinder the path of way of light. Okay, so again, when the light passes through this, this is simply the movement of light throughout the cavity without any say change in the polarization. So again, this amplifier is something that increases. Just a second. Yeah. So this amplifier is something which increases the intensity of light, so and so on. Now what happens immediately when it reaches the maximum value? Okay, for your convenience, I will draw this diagram to be more clean. See, this is the situation of total loss. Slowly what happens when voltage is turned off, what you do is the loss has its maximum value, but slowly the gain in the system increases because of this amplifier and voltage turned off. Now this gain has reached the maximum value. What happens is as soon as this reaches its maximum value, what you do is you immediately turn on the cavity. And therefore, what happens is immediately the gain which had reached the maximum value tries to drop and reaches a minimum. The loss also, as the gain, similar to the gain, as the gain reaches the maximum value, the loss also reaches to a zero. And when the gain reaches to zero, there is a new giant peak coming out as the output, and this is the giant pulse. Okay. So now what I want to say is initially, yeah, initially if when the voltage is on for the focal cell, say we have a vertically polarized light at this. Okay, when it passes through the focal cell, it diffracts at an angle that is 45 degree. Okay, now after that it passes through this, gets diffracted back here and again passes through focal cell, and therefore it turns something to be horizontal, that is 90-degree polarized. Now here what we were asked is in the example discussed above. So first of all I have also explained you what the example we had discussed in that module. What was the example? So that example was something like how is the Q switching done by a focal cell? And what does the focal cell do? The only thing that focal cell do is the polarization or change in the polarization. When this change happens, that is the reason how amplifier at a certain angle is able to reflect and how this principle of loss and gain comes out. Okay, now here say the polarization in the Q switch, we have talked about the angle that is 45 degree. Here we have also told that suppose the initially the light is vertically polarized. Soon what happens after passing once in the one round and the second round, what happens? It becomes horizontally polarized. Okay, and this can happen only when the focal cell does deflection at 45 degrees. Say if it is at 22.5 degree, no, that thing will not occur. The total will be 45. Then the total case will be 45 degree. But in this case, the total is 90 degree. Okay. So in the example discussed in the course, the focal cell acting as a Q switch rotates the polarization by 90 degree. Okay. Now here one more thing to discuss was, suppose here we have given a pulse light to the source and it passes through this Q switch and our arrangement. What we get at last is a giant pulse. Okay. This giant pulse is what we get. So this is the only thing we want to say is, in this case as a Q switch we can get something which is pulsed, and second thing has a higher intensity. So this is the main application of this focal cell working as a Q switch, which rotates at the angle of 45 degrees. Okay, this is the right answer for our question. If you have any doubt in this question, we can discuss and then we'll proceed to the next. Yeah. So coming to question number 5. In the Tracy geometry and Martinez geometry, chirp introduced by the stretcher and compressor is positive in both cases, negative in both cases, positive and negative respectively, negative and positive respectively. Okay. So, first of all, what is the Tracy geometry and what is the Martinez geometry for a stretcher and compressor? Stretcher or compressor. For a light beam, say you are giving a pulse that is like this. Okay. Now, stretching, as the name suggests, the pulse will become something which is stretched. Okay. So, with respect to time, the we'll get a broad line, okay, which has the more number of wavelength in values of wavelength. And talking about compressor, further we'll get this. Compressor means we will get something. Okay, yeah. So we'll get something that is more compressed than our incident. Okay, so this is something which we can get. Now, what a Tracy geometry and Martinez geometry is. Basically, Tracy, the geometry shows the arrangement. Now, how is the stretcher and how does the stretcher or the compressor works? On the basis of that only, or on the principle of how or what change we want, and how do we want the stretching or compression? That is how we decide what should be the arrangement of the mirrors. So in the Tracy geometry, here we have a picture of what Tracy geometry is. See, we introduce earlier we had seen that what happens when this we introduce a grating. Okay, say this is the incident light which is shown by this dotted lines. It goes through this goes straight through this grating. Okay, because of this grating, the light beam gets deflected at different angles. Therefore, say we had a particular pulse, now it is separated on the basis of the frequency because of this diffraction grating. Because of this grating, say one of the or and this diffraction is also called as the chirp, which is induced. Now, because of this chirp, say it passes through the another grating. Okay, through the another grating, when it passes, it is again diffracted and goes straight. Although we can say that, say this act as something, a grating, it gets diffracted at certain angle. Say if it passes through that, it goes from this angle to this angle. When it passes through the grating, uh, it again incidents on a plane mirror. From the plane mirror, it is diffracted back to the grating, and from the grating, it goes to the another grating. And here, see both of them, they incident together on the final one, and thus they are separated into a stretched beam. Okay, so this type of arrangement, if you talk about, say this is the pulse beam. Okay, when it is incident on one grating, then the second, then a plane mirror reflects back, then goes to the back to the way we get a stretched pulse beam as an output. So this type of arrangement where we use two gratings, one plane mirror, this hole is called as the 3C geometry. Okay. See, the going to more specification of this arrangement. First, what we could get is the the blue light, it is ahead and the red is backward. Say something with higher frequencies forward, and that with the lower frequencies backward. Okay. So this particular case is called as the negative charge. Okay. First of all, the light with a fixed frequency is chirped. So that is intentionally chirped, and that too negatively chirped. Then in this case, what happened? The larger frequency lead and the smaller frequency trail. So these are the two more specifications of the Tracy geometry, which we'll study later, that in Martinez geometry does not happen or something change happens. Therefore, basically it can work as a stretcher and the compressor as well. Now, if I incident it with two beams or just change the arrangement to some extent, then this whole arrangement can also work as a compressor, where two beams that have a different path length or speed, they can come together to form a single beam. That is a pulse beam. Okay. So three specifications we discussed for this is, first of all, if you pass an unchirped beam as an input, pass through the diffraction grating, which then passes through the other diffraction grating. Because of the first diffraction grating, first of all, the two beams are diffracted at different angles. Because of this diffraction, again, when these diffract at different angles through the another grating, they get reflected back. And since they are already diffracted, uh, they go straight through a plane mirror. When they go straight through a plane mirror, they are reflected at certain angle. When they are reflected at certain angle, they come back to the grating and then again incident on the another grating together. When they are incident together, the total beam what we get has is a stretched one, which has different components separated and are at different time and come at a different time. In this whole scenario, the larger frequency they lead or they are ahead of some with the lower or the smaller frequencies. This whole is called the negative chirp, which is induced in the 3C geometry. Now, what is the principle of this 3C geometry? Why are we doing all these things? So basically, if you have a pulse laser, if you pass it through a stretcher, okay, say this arrangement, you get a beam like this. Then you pass it through an amplifier. Okay, during the by passing through the amplifier, this beam this increases in intensity. Say this. So this is the thing amplifier does, and then you again pass it through, say something called compressor. Okay, when you pass it through the compressor, you get again a sharp short pulse of laser, and that is amplified in intensity. So basically here we are using this chirping, we are using this drawback as an advantage to amplify the intensity of the laser beam. and this is quite interesting phenomenon as well. Second thing that is important to discuss is 3C geometry introduces negative chirp. Second thing, the larger frequencies they are ahead and the smaller frequencies they are low. Although this is represented pictorially, this does not say that we are using a visible range of light and or you can say that this is definitely a blue one or a red one. This normally indicates that the beam of light or the part of light that is ahead is something with a larger frequency, and the one which is back is something with a smaller frequency, and therefore we get such a broad band. Okay, when this broad band, how does it go out now? How does it go out? Although we can see in the picture that the two are overlapping each other, but in the figure the two are close to each other, they do not overlap. So here where this stretched beam comes out, we keep a plane mirror for its reflection, and in it this stretched beam then get reflected. Okay, and this is the output beam, which is more stretched. The point to remember is if you pass the input as the unchirped beam, when you pass through this entire geometry, you will see that the output beam is a chirped one. When the output is a chirped one and the input is the unchirped output, it works as a stretcher. For the same a type of arrangement, if you said that the input is chirped and the output is unchirped, then it acts as a compressor. Division of the chirped and what is unchirped, we could say that when you pass a high intensity beam through a medium with a refractive index N1, what happens is due to this high intensity of beam, the part of this beam is split into its components. Okay, these components these components in the output beam are separated enough, and therefore this process is called as the chirping. Okay, what is it called? Chirping. This process is the thing that we will further use for the amplification of laser. Okay, now first we had discussed that the chirp introduced by the stretcher or compressor in 3C. So the chirp introduced in 3C geometry is negative first of all. Okay, so for this we got the answer so far, that in the case of or negative in both cases. So these two can be the answer, A, this or this. Now going to Martinet geometry. How is it different from the 3C geometry? And in when it works as a stretcher or a compressor, how does the change out? So basically here the arrangement is quite different from the one. First of all, or you can say this is somewhat opposite to that of the initial what we called as 3C geometry. Yeah. So when you introduce a positive, uh, when you introduce a light beam, this is a reflecting mirror, and these mirrors are generally totally reflecting mirrors. Okay, this totally reflecting mirror, then this light beam passes through diffraction grating. When it passes through diffraction grating, again as I said, it is split into three components. Say here they have indicated it as red, green and blue. Now after passing through this, they pass through a lens. Okay, when they pass through this lens, when they pass through this lens, this is a convex lens, they go straight because these two are kept at the distance of focus. Okay, when this goes straight through this, it again passes through the another lens, and now this diffraction grating is kept at the focus. Okay, so what happens is they again pass and converge at the focus as we had studied in the ray diagrams. When it converges, it just reaches to this reflecting mirror. The second thing is earlier, if you would have observed in 3C geometry, the two diffraction gratings are kept like parallel to each other. But in the other case, say in the second case, these diffraction gratings, okay, are at acute angle to each other. Second thing, first fact. The second fact is we have to keep lens on the way, which is again something that reduces intensity. If you would have seen, say this is the point, say this is the mirror, you can see that at this particular point of time, see the red, if you talk about time, say this is the time, it introduces a positive charge. Okay, so using this pair of gratings, we can introduce a positive charge. What is a positive charge? A positive charge is when the smaller frequencies they lead and the larger frequencies they trail, or the larger frequencies they are behind while the smaller frequencies they are ahead. Okay, so this is the case. Got it? Now, uh, this also act as a pulse stretcher. Why? Because see, initially say the intensity of the beam was like this, the pulse was this, and now what you get is something with each component is a little bit separated or spread. So in the 3C geometry, as I could say that we could get a negative chirp. The negative chirp prefers when the smaller frequencies are behind and the larger frequencies are ahead. The second case is of the Martinez geometry, where the smaller frequencies they are ahead while the larger frequencies are behind. So this is a positive chirp. Now here in the question, in the DC geometry and the Martinez geometry, chirp introduced by stretcher or compressor is first positive in both cases. So no, in the first case itself we got it is negative. The second is negative in both cases. No, but in the second case we found it to be positive. The third is positive and negative respectively, but no. In the case of 3C geometry, we could get that it is negative. So these three options are incorrect, and only this one, the negative in the first case and positive in the second case, are the correct options to this question. Okay. If you have any doubt in this question, we can still discuss. First of all, in the 3C geometry, the arrangement of the mirror, the gratings, not the mirror, they are parallel to each other, while in the Martinez geometry, these are at an acute angle to each other. In the first case of the 3C geometry, we could see there was no use of any lens, but in the Martinez geometry, they have used lens to converge the light. Although you see that after this we have used only a plain reflecting mirror, which on the other hand they have used at the last, and they have used two reflecting mirrors. Okay, and also we could see that in this whole case the blue light or the larger frequency light was ahead while the lower frequency light was back, and this is called to be as the negative charge, while in the second case, we could see that despite stretching, the smaller frequencies were ahead while the larger frequencies were behind, or they used to trail. So this is the whole summary of this. And the answer to this question is the chirp that is introduced in case of 3C geometry, that is negative, and that of in case of Martinez geometry is positive. Okay, this is it. Now, question number 6. Multi-pass and regenerative amplifiers produce pulses that are of equally short pulse and lower power in both cases, equally short pulse and high power in both cases, shorter pulse and higher power respectively, higher pulse and shorter power respectively. Okay, so actually what this multipass and regenerative amplifiers is, actually initially when we studied, I told you what was the this stretcher and compressor means. So basically chirping is the thing that we make use of. Okay, so what we saw initially is, first if you have a pulse laser say of this intensity, we stretch it to like say this extent. Then after we pass it through an amplifier, so we get a stretched amplified output, that is say this. And when we pass it through the compressor, we this whole thing is compressed to a beam with a larger intensity, and that is amplified as well as compressed. Okay, so this particular thing is called as the stretching. The stretcher setup, we could see, that is the Treacher geometry and the Martinez geometry. The second thing is amplifier, and the third thing is compressor. Okay, so these are the three things which are used to amplify the laser, and what they make advantage of is the chirping. Okay, now see, here I have put a diagram of the multipass filter. Although it looks a bit complicated, but we can simplify it and discuss. See, initially, this is the seed. What is the seed now? The seed is the incident chirp laser. What is this? This is chirp. And see, what we had discussed is, from the stretcher we get the chirped form. Okay, chirped output. And even through the amplifier also we'll get a chirped output only. Only the compressor is the thing that converts this chirp to unchirped. What is this chirping? Chirping is like separation of the each component of that laser, and therefore give a broad band. So basically, when the seed is incident on the gain medium, it passes through M1. Okay. When it passes through the M1, see it is reflected at this angle and passes through M2. When it goes through M2, it again passes through the gain medium and passes through M3. When from the M3, it again goes to M4, and through this reflecting setup again from M4 it goes to M5, and meanwhile it goes to M6 and then again to output as the amplified chirp pulse. What thing we missed here is the pump. Okay, so this pump is something which is used for the amplification within the gain medium. As you can see, the first round when it passes through M1 then M2 second, then again M4 to M5 third, and then M6 to M4 fourth. So basically, it does four total rounds throughout the gain medium C. And during all these four rounds, it passes through the gain medium and is amplified when it passes through the gain medium. Why is it called the name multipass? Why? Because see, you can see there is a large setup of many mirrors that reflect to each other and again pass the light back to the gain medium. The purpose of keeping all these mirrors is the only fact that the number of mirrors you keep, the more times it passes through gain medium and gets amplified. Okay, so here is the pump that is responsible for the amplification and this gain medium. The other mirrors which are helping in bringing the reflected light back to the gain medium. So here, as you can see, the chirped beam, which is act as the seed, the result or the output beam which we get is something which a very high intensity, but it is still chirped. What is the thing is, we can by passing through these reflecting surfaces. See, each one is a reflecting surface, so the net time is not reduced, and therefore we can get very short pulses in the case of multipass amplifier. So the advantage is, first we get the amplified chirp pulse, and that too is very short pulse. Okay. Again, I'll repeat this whole process. The first thing is the multipass amplifier. First of all, we had seen that why is this amplification and how is it related to the stretcher and compressor. So first of all, the amplification in the case is done using some stretcher. First of all, the beam of light which is unchirped, when it passes through a stretcher, is becomes chirped and broad. When it again passes through the amplifier, this chirped beam, which has a low intensity, is converted to a chirped output beam with a higher intensity. When this whole process occurs, the chirped output beam is again allowed to pass through a compressor, and this compressor converts this chirped output beam to unchirped one with a still higher intensity. As we can say, the area remains the constant. So first of all, we had two type of amplifiers. The first was a multipass, and the second is one is regenerative. How does the amplification occur in each of these, which we had discussed here? In the multipass filter, first of all, the gain medium has a pump probe attached to it. The gain medium, we can say, is something which is the titanium sapphire laser or other medium. Okay. In our case, we are feeding it with a curved laser, that is a C. When this curved beam passes through, it goes on through a series of sets of mirrors which reflect the light back and forth and then pass it through the gain medium. The again and again, the number of times it passes through the gain medium doing the rounds, its intensity is amplified. Further on, finally, after passing through M6 and passing through the gain medium, what we get outside is the amplified chirp pulse, which is the output. If you want me to summarize it, I'll summarize the other because it is quite scribbled one. So we'll look again at what is happening here through this series. First of all, we have first first of all we have what we have is a C, that is a chirped pulse. Okay, this chirped pulse goes through the gain medium. Gain medium is something a crystal, that is a titanium sapphire laser or something. When it passes through the gain medium, it goes to the M1. Okay, if you can see the way, this is the M1. From M1, it is reflected to M2. From M2, it goes back straight to the M3. From M3, it is again reflected and goes to M4. Another totally reflecting mirror. From M4, it again goes to see this path, and this is the M5. From M5, it again goes to M6 and passes through the gain medium. In each cycle from M1 to M2 to M2 to M3, say in the first round from the C to gain medium, this is the one round. In the second round from M2 to M3, this is the second round. From M3 to M4 to M4 to M5, this is the third round. And from M5 to M6 and M6 to just output C, this is the fourth time. So see, it passes through the gain medium four times. Meanwhile, this pump, what it is doing, this is doing the function of pumping, and that is the amplification. And when each time it passes through this gain medium, there is increase in intensity. And each time there is increase in intensity, we get what is the amplified chirp pulse. One point to note is what is the if the if the incidence beam is chirped one, the one which we get in the output, that is also a chirp pulse, that is not an unchirped pulse. Okay, got it? Now second one what we got is regenerative amplifier. Regenerative amplifier, this whole setup is looking quite simple. First of all, here there is a pump. This is a pump laser. This pump laser passes through the gain medium. It has the only function for the amplification. Second is the seed laser. When the seed laser incidents on the gain medium, what we can see is it it passes through the gain medium, goes straight, and then reflects through this mirror. Then again it passes through the gain medium, passes back and forth, to and fro, and again goes out. And in result, what we get is by passing through these plane which mirrors which are parallel to each other, the output we get is of high power. Okay, by passing through this thing, this entire setup, we get something which has a more power. Okay, so first of all, amplifier is used to increase power of laser. Say we want it from say 10 to the 10 joules to 10 to the power 4 joules, and this is the thing what an amplifier does. Okay, so first of all, coming back to the question, multipass amplifier. When we talked about multipass amplifier, we could study that since there is only one gain medium and the other are mirror, there is no lagging off in the time, and therefore we can get a short pulse and not a broad pulse. So this is the advantage of a multipass filter, that way we get a short pulse. So short pulse and shorter pulse. The second thing is regenerative. We do not, in this case, we get a higher output power, which unlike in the first case, we could not get in case of multipass amplifier. So basically, here the answer will be high power and shorter pulse respectively. Okay. So this is the answer to this question. The other three, these are. If you talk about higher pulse and shorter power, so this is not the answer because what we have studied is just the vice versa. Okay. Yeah. So now we'll go on the question number 7. If you have any doubt, we can stay for a minute and discuss the queries. Then on, we'll go to the next question. Yeah. So question number 7 says repetition rate of the output of an amplified laser is determined by the repetition rate of the first option is seed pulse, second is pump laser of the amplifier, the third option is focal cell, and the fourth option is compressor. Okay. So in this setup, what we had taught, say in both of these setups, these are the two amplifier cases given to us. Okay. When we talk about this amplifier cases, what we could say is, see, the output, say this is the output of the beam. Okay, and in this case, this one is the output. Yeah, this one. So there is something called the pump, which is working along the pump laser for the amplifier, and the one is the seed pulse. Now, repetition rate of the output of the amplified laser is determined by repetition rate of the, so whole soul, the amplified laser, its repetition rate or the output, it basically is affected by something that is the seed. Here there is seed with some repetition rate, and after that when it the number of times it passes through the gain medium, the pumping that is affected or the amplification is affected by the repetition rate of the pump laser. Okay, so if you want to say that what is the thing that affects, so we can just say that the repetition rate of this amplified laser, which is the output, that depends only on the repetition rate of the pump laser. Okay, so these are the wrong options because there is they do not have any inherent incident light with them and the seed pulse. So the output that will totally depend on the pump laser of the amplifier. Okay. If you have any doubt in this question, we can discuss and then we'll proceed to the next one. Yeah. So I think we should go on to the next question. So what our next question says is, after the stretcher, the laser pulse is curved of the same peak power as seed, of the lower peak power than seed, or of the higher peak power than the seed. Now, see, first of all, I'll just give an idea to this question and we'll come to the answer directly without any problem. First, say in the case of stretcher setup, we say a single grating setup. Grating refers to the diffraction grating. Okay. So first is C. Here I incident or the input is this incident B. Okay. This incident B goes straight and then it incidents on a grating. Say this grating looks like something like this. Okay. After incident, because of the grating, say this has different component, it is split and therefore is diffracted at different angles. Okay. When it is diffracted at different angles, say this one is the one which is blue and this one is the one which is red. Okay. Now again I have a concave mirror which is blue. This concave mirror is something like this. Okay. And it will reflect the light. So say this arrangement is not very proper. I will read about it. Yeah. So when it passes through this way, say this, it goes straight. It goes straight, and then the because of the diffraction grating, say this, it is refracted. When it is diffracted to two components, say one is the red and another one is the blue. Say this is the blue and this is the red one. When it goes through this way, there is a mirror, that is the concave mirror, the totally reflecting mirror. Okay, because this concave mirror, what they do is, see, this is again reflected at certain angle and this red is again reflected at certain angle. Then again the two is incident on a totally reflecting plane mirror. When you talk about totally reflecting plane mirror, the light again passes at certain angle. Okay, and this way when it comes out, it is in the form of, say, this straight beam which has such a broad intensity with respect to time curve. Okay, and this process is called as something called as chirping. Okay, what the chirping is? Chirping is something like when the focus beam of incident light that passes through a medium, because of this high intensity, the change in refractive index occurs and the light gets diffracted into different components at various angles. And this is what has happened in the stitcher. After the laser pulse, they say this one, it passes through the stretcher. This is say the input. What we get the output is this. Okay, and yeah, we can directly say that if we pass on something unchurned, that this thing we had also discussed earlier. If we pass something unchurned, what we get as output. So here I'll write the answer. In case of stretcher, say input, if it is unchurned, the output is equals to churned. Anyway, we also know that the say the area of curve remains constant. Since the area of curve remains constant, we can say that the peak power, and here what they are asking as seed is this input. Peak power of seed is more than output. So after the stretcher, the laser pulse is chirped. Okay. So first of all, chirped is the right option. Why? Because it is distributed into different components. The second thing is of the same peak power as seed, no. Of the lower peak power than seed, yes. And of the higher peak power, no. This is also the wrong answer. Why? Because the total area remains same. Suppose we talk about a triangle. Say this one triangle and this one triangle. Okay. Suppose say that area of both is same. So area depends on half base into height. If you increase the height, if you want to keep the area constant, you need to decrease the base. In this case, the base is increasing, so the height is decreasing. Okay. Therefore, we get a lower peak power than the sea. What does this intensity says? This intensity says the number of photons. Okay. So basically here whatever we use are totally reflecting parts. This diffraction grating, concave mirror or a plane mirror. Each of the part is a totally reflecting part and therefore the number of photons or the count is constant. Okay, is constant, does not get increased or decreased. What changes is the peak power. The peak power for the output beam is lower than that of the C. So this is the purpose what a stretcher does. Now conversely will happen in case of the compressor. What happens in the case of compressor? Say this is the chirped beam. Now If you remember, so far I have discussed that what is the phenomenon or what are the steps involved in the amplification of laser. Say the input beam is something like this. First you pass it to a stretcher. Okay. When you pass it to a stretcher, it gets broadened. Second thing what happens? You pass it through an amplifier. If you can name it, we studied two, the multipass amplifier, and the second is the regenerative amplifier. So in the case of the amplifier, see the intensity is say broad. Okay. This is thing what amplifier does. After being amplified, it is passed through a compressor, which again gives a beam that is unchurned, okay, but of a higher intensity. Okay. Now, after the compressor, the laser pulse is chirped first of all. So no, what the compressor does is that converts the chirped beam of light to unchirped. The second is of the same peak power as the seed. What is the seed here? This is the seed here. Okay. Or say or input. If you want to talk about this, seed or input is something whose amplification we need to do. So same peak power as the compressor. If you just see the if you can just infer from the picture, you can say that it does not have the same peak power. The third was of the lower peak power than seed. So is it of lower peak power? No. This is also the wrong answer. And of the higher peak power than seed. So yes, this is the answer to our question of the higher peak power than the seed. Okay. If you If we talk about compressor, so compressor is the same as we have talked about. Just we have to invert the functions. Okay. Suppose we give suppose we give a chirp laser with this much intensity to a structure. Say this is the reflecting mirror. From it passes through the concave mirror and then it passes through something. Say grating. All these converge into through a then again a mirror. These will converge to a single beam of light that is highly amplified. Okay. So in short, with the summary, stretcher, unchirped to chirped with higher, sorry, with lower peak power, and okay, here I can write. Okay, what does a stretcher do? Stretcher converts unchirped beam to chirped beam. What happens? Lower peak power. Why? Because the number of photons remain constant. Second is using the amplifier, low peak power chirped beam is converted to high peak power chirped beam. This is the function of amplifier. To amplify. To, and what we talked about is the repetition rate of the output beam depends on the repetition rate of the pump laser. The third thing, what happens? We cannot use this chirp beam for our purpose. So what we use again is compressor. We use compressor which converts the chirped high peak power to the unjob low peak power. Oh, sorry. High peak power view. Got it? So these are the three: stretcher, amplifier, compressor. And the summary of this module was that we had studied different kinds of stretchers, the different geometries. The first was the Tracy geometry, the second was the pulse stretcher, that is Martinez geometry. Each one had one advantage, one disadvantage, and one different specification from the other one. First of all, the Tracy could get a negative charge, and in which the larger frequency is led. In the Martinez geometry, on the contrary, we could get a positive charge where smaller frequencies could lead and the larger frequencies could fail. The third is Q switching in the bifocal cell. How is the Q switching attained? By the Q switching, we can get a giant pulse directly from the input laser. What we use is a simple setup of an amplifier, a mirror, and a partial reflecting mirror and a focal cell. Basically, what they do is when the voltage is on and off the focal cell, it polarizes or changes the direction of polarization of light. When the voltage is off, the light it simply acts as a medium where light can pass to and fro. When this further happens at a maximum peak of height, when this is finally done, what they do is with this turn the voltage on. As soon as it is on the focal cell, it polarizes the light in one direction and to the other, and therefore causes a 90-degree rotation in the polarized light, which can then not pass through the amplifier. When it cannot pass through the amplifier, it is directly reflected back. Because of this reflection, we get an output beam which is a giant pulse. Giant pulse refers to something which is of higher intensity. Okay, so this is the principle of Q switching. Focal cell, it is also called as the electro-optic modulator. So electro-optic modulator is something which is used to modulate the frequency of the incident light, and this does by changing the polarization of it. Okay, what is the angle that is used by the focal cell what is the angle at which the focal cell rotates in Q switch? That is the 45-degree angle. What is cavity dumping? So cavity dumping is a process in which we can just separate the light frequencies of beam. It is split to E1 prime plus E2 prime. The value of the total intensity we could get from this expression. In this expression, the total intensity is the mod square of the electric field of the output beam, which depends on this. And this is the modulating function, phase modulating function, whose maximum and minimum values are some integer and k plus half respectively. So this was the first question from the second. If you have any doubt in any of these questions, you feel free to ask, or else we'll just finish this session. Here we have written the basic summary of a stretcher, amplifier, and compressor, which covered the most of the part of this week's module. And these are the different arrangement: the multipass amplifier system and the regenerative amplifier system. These are the amplifier systems. So far, we have discussed the 3C geometry and the Martinez geometry are certain arrangements for a stretcher. Then what happens to the pulsed laser when it passes through a stretcher, when it passes through a compressor, and when it passes through an amplifier? That also we had discussed. I'll give a time of 2 minutes. If you have any doubt, you can ask. Okay, so we'll end this session. Thank you so much for joining.